Okay, we're on air. All right, so I'm going to give you some theoretical framework for the slice filtration, and then I'm going to give you some illustrations with slides. So, okay, so here's a definition. A localizing subcategory tau of a topological model category M is one that is the subcategory that's closed under three operations. One is weak equivalence. Two, cofibers and extension. So what I mean by that is the following. Let's say this is a cofiber sequence, W to X to Y to Z. And the first guy is in our subcategory. Then X is in there if and only if Y is in there. Now, I am not requiring that if X and Y are in the subcategory, then W is in the subcategory. That is not part of the definition. It's closed under, so when I say cofiber sequence, Y is the cofiber of this map. And when I say extensions, I mean, if these two objects are in the subcategory, then the middle one is also. But I repeat, I'm not requiring that if X and Y are in it, then W has to be in it. Now, here's an example. Tau is the set of n connected, or let's say n minus 1 connected spaces or spectra, depending on which category you're in. That's an example of a localizing subcategory. So,
so you're thinking of a full subcategory, you just specify objects?
Yeah, it's a full subcategory. Yes, thank you. Full subcategory. Okay, so you see, if these two spaces are n minus 1 connected, that doesn't make this an n minus 1 connected space. So
The other way around does.
exactly. Okay. Now, to continue this discussion, tau is generated by a set T of objects if it is smallest full subcategory containing T and closed as above. Oh, I left out the third condition. Sorry, wait a minute. I'm getting ahead of myself. There's a third condition I've got to put in. Third condition closed under arbitrary coproducts. Okay, so then tau is generated by a set T of objects if, now what I was saying before, smallest full subcategory containing T and closed as above, closed under these three operations. Now, in this example here, this is generated by the set with one object, the n sphere. Every n minus one connected space or spectrum can be formed from the n sphere by doing these things. Now, you don't lose any generality by assuming that T just has one object, because if T has a bunch of objects, you could take the coproduct of all of them, and that would do the job. But in practice, that's not convenient. It's not convenient, because you've usually got a bunch of objects, and you want to deal with them one at a time. You don't want to throw them all together. Okay, now it's time for a theorem. If M is, now technical hypotheses that I don't want to mention, and tau is generated by a single object T, let F be the unique map from a point to T. Then there's something called Dror-Farjoun. There's something called Dror-Farjoun localization. It's a form of Bousfield localization in which, now remember what Bousfield localization is. You start with a model category satisfying some mild hypotheses like these, and you expand the collection of weak equivalences. And then you look for a new model structure that has the same cofibrations that you started with, but fewer fibrations, because since there are more weak equivalences, there's more trivial cofibrations, and there's more trivial cofibrations that fibrations have to have the right lifting property for, so it's harder to be a fibration than it was before. It was harder to be a fibration. So you get a new category that has the same cofibrations, more weak equivalences, and fewer fibrations. So I'm going to do this in the particular case where I'm going to declare this map to be a weak equivalence. I'm going to assume that's a map. Yeah.
Maybe many of your examples are pointed.
Yeah, these are all, yeah, I should have said that, pointed. Yeah, let's say everybody's pointed. Yeah. Everybody's pointed. Okay, so so there's a unique map from the initial object to T. I don't really need pointed. This could be the empty set if it was. But anyway, this.
Well, then you do T2, you take
No.
the other map.
Well, I could, yeah, I guess so. I guess so, but yeah, I do the other map. You're right. Anyway, we should just do that. That would work just as well. Okay, so then, so this is the unique map So then there's okay, so this is a form of Gauss field localization that was studied by Emmanuel Georges Farjun, who wrote a book about it in 1996, so that's why I'm calling it Farjun localization. So I'm going to give this, okay, I'm going to write this as P upper tau, and this means this is the notation for the fibrant replacement functor that's in this new category. Now, so you can always do this. Now, let's go back to our example. We can do this in this example. What do we do? It's the n minus first Homotopy section. So the fibrant replacement in this game is the n minus first Homotopy section. So you kill all the homotopy groups from dimension n and up, and that means that pi n of everything in here is 0, and so pi n and higher of everybody is 0. That means, so if this was the n sphere, this map induces, so let's see. Yeah, this is always a weak equivalence, and this is supposed to be contractible. So in other words, this is always contractible after you do this localization. And if I do this kind of localization here, if I kill all the homotopy groups from dimension n and up, that means that means you don't have any maps from Sn or anything that can be built out of Sn. Okay, now there's also, okay, so this means you can okay, so back to this example. I can do this for any n. So let's say Pn is the nth Homotopy section. So for any x, you get a tower. It's a diagram that looks like this. So you have a diagram like this, and you can look at the fiber of this map. So this is the map obtained by, this is the guy you get by killing all homotopy groups above dimension n. This is all homotopy groups above dimension n minus 1. And the difference between the two, I'm going to call this. This is by definition the fiber of that map. So in the example at hand, this is going to be an Eilenberg-MacLane spectrum that captures the nth homotopy group of X. It has one non-trivial homotopy group, the nth homotopy group of X. And when you have a collection of functors, so you have a collection of in this example, we get a collection of localizing subcategories. How then, and when you have a collection like this is known as a T structure. Forget what the precise definition is. It's when you have a bunch of categories like this that are related in a suitable way. Now, why am I doing this? Because I want to generalize this to the equivariant world. So, so I'm going to give you another example besides this one over here, the equivariant example. So, okay, the equivariant case. So G is a finite group. The category of interest is the category of orthogonal G spectra. Now, I want to define a sequence of localizing subcategories in here. So I need substitutes for spheres to generate my localizing subcategories. So here's a definition. So if I have for each subgroup of G and integer m, I'm going to define S hat MH to be one of two things depending on the sign of the integer. And that is for m greater than or equal to 0, it is the following. So rho H stands for the regular representation of H I can take m copies of it and build this and form the sphere, the representation sphere. That means the one-point compactification. So this gadget is an H space, and then I smash over H with G to get a G space. So this is a wedge of G mod H copies of this thing with G acting accordingly. And fudge a little bit. What I really mean is the suspension spectrum of that thing.
So you really want the regular representation including the trivial?
Yes, I want a regular representation. That's exactly what I want, yes. Okay, that's for non-negative m. Now, for negative m, it's this. Now, what do I mean by S minus MH, M rho H? I mean a Yoneda spectrum. Now, a Yoneda spectrum is defined as follows. I have to tell you its W component for every representation W, and it is it's this. This is a certain space defined by Mandel and May that I've described in earlier talks. This is a tome space of Stiefel manifold. So V and W are representations of H. I'm describing this spectrum that I call S minus V. It's a Yoneda spectrum, meaning it's defined by a Yoneda functor. Constanza, you look
I
puzzled.
think if you're going to write down for m less than 0, you're still meaning s. You don't mean
You mean-
minus m on
You
the
want
sphere
n to be
because-
greater than 0.
Oh, yes, I
Yeah.
do. Okay, so I guess I mean this, yes. Okay, you're right, okay, yes. Okay, so m is negative, so this is a negative representation, and that's what I mean. Okay, this is a well-defined spectrum. Okay, so I get these gadgets, so I'm gonna call these things slice spheres. Now, if we were in the case of a trivial group, these would be just ordinary spheres, as you usually understand. Now, I want to get a T structure, so I want to get some localizing subcategories out of this. So So I'm going to define a set of objects now, Tn upper G, and it is the following. I take these gadgets that I've just defined, and I require that m times the order of h be greater than or equal to n. That is a collection of objects in, these are all spectra. This is a collection of spectra. And so that I can define tau and G to be the full subcategory generated by these things. And that leads me to functors like this. Well, let's see. I'm going to give this category another name. So the name is orthogonal G spectrum, where the subscript is greater than or equal to n. So it means that things that can be built out of, so I assign a dimension to each one of these gadgets, and the dimension is that of the underlying spheres. This thing up here is a finite wedge of spheres, and the dimension of each of those spheres is m times the order of h. And I want the collection of all these slice spheres where this number is at least n, is n or greater. And then I'm going to say this. Spectra Y with SPG X, Y, contractible for all X in the category I just defined. So this is the analog of co-connectedness. So I want all, so this means no homotopy groups in dimensions n or above, where homotopy groups are understood to mean maps from these things into it.
You want this the other way around?
What?
The x and y, should they be switched?
I don't think so. I mean, think of these as, you're supposed to think of this as a Postnikov tower where there's no homotopy above some dimension. and these are spheres. So yeah, no, I want it like this. So x is in here. Think of x as something that's n minus 1 connected. And
Okay.
think of y as something this is a co-connectivity condition of y. But no, that is what I mean. Okay, so now we can get a diagram like this. In fact, I will. Each x a tower. And then you can take the fiber of this map, and I'm still going to call that Pn of x. I run out of room to put the g unless I want to put it over here. Anyway, this is the nth slice of x. And in favorable cases, this could be an n-dimensional a wedge of n-dimensional slice spheres smashed with the integer Eilenberg-MacLane space. Remember, in the classical case, the nth layer in the Postnikov tower was an Eilenberg-MacLane space that picked up one homotopy group of the thing. In this case, it could be a wedge of these slice spheres of the appropriate dimension smashed with some Eilenberg-MacLane space. So we get a spectral sequence out of this. Now, some comments before I proceed to the slides and the illustrations. If we forget about the group action, we took everything in sight and forgot about the group action, then what we'd be constructing is the ordinary Postnikov tower of X. Carefully secured myself a box of chalk. And now I don't know what I did with it. Okay, now, I should have mentioned here that E1 SV is pi V minus S of P So V is an n-dimensional representation. This group is this. This is equivariant homotopy, so it's actually a Mackey functor. This is a spectral sequence of Mackey functors. Okay, so if you forget the group action, you're just looking at the ordinary Postnikov tower. In the case of Mackey functors, that means you look at the bottom of the Lewis diagram where you're just thinking of the G set you're looking at as G itself. Then you get the ordinary Postnikov tower. Second comment. It's very rare that you're actually going to know what these homotopy groups are. We rarely know what this thing is. But in the cases that Hill and Hopkins and I study, when the spectrum involves something related to MU, we have access to these groups. Okay, now it's time for my first slide. So, yes. Okay, now, okay, this is a picture of the slice spectral sequence. And the point of this picture, let's see, this is a projector problem. The spectral sequence is concentrated in the first and third quadrants, which is weird. These regions are supposed to be shaded in gray, but it doesn't show up in this because of this projector. But anyway, the contribution of an individual slice lies along a line like this, and this is a vanishing line of where the slope of the vanishing line is 1 less than the order of the group. So if this looks like it's about 3 to you, this could be for the group C4. Anyway, you have these vanishing lines. Everything's either in the first quadrant or in the third quadrant, and there are these vanishing lines. There's this vanishing line where the slope is 1 less than the order of the group. Now this is I want to point out how peculiar this is. This means, this is for any G spectrum X. This means you might think that if you took your G spectrum X and suspended it umpteen times, you would just be moving the whole picture to the right. That's what usually happens. That's what happens with a classical atom spectral sequence. You have the atom spectral sequence for something, and then you suspend the spectrum you're looking at. You're just sliding the whole picture to the right. That is not what happens here. That is not what happens here.
Actually, what is T here? Degree of V?
T is, well, in this case, it's an integer, but yeah, T is,
V
we have an
is-
ROG graded spectral sequence. This is an integer graded version of it. So T is, think of T as an integer, a trivial representation of degree T. Think of it that way.
Okay, we gave it an E1 term graded
had-
by
he had a-
S
okay.
and V, so I thought maybe T was just the dimension of V, but not.
In general,
You're saying it's the trivial part of V instead.
no, I'm saying that in general, T is, T would be something in ROG. We are looking
Yes,
at
okay.
the case where
You're
T
taking-
happens to be
yeah.
trivial.
Okay.
Now, there's
Yeah, you're
other
just one
pictures
plane.
like,
Very good.
yeah, there's
Thank you.
other pictures like this where T could be something other than a trivial representation, in that case, the vanishing lines would be different. It would be a different picture. But anyway, if you were to suspend this x here umpteen times, the picture you would get would not be this picture slid x umpteen units to the right. It would be something entirely different. And the reason for that is where are we? Yes. Okay. Okay, so I've erased my definition of the slice spheres, but anyway, these slice spheres were defined in a certain way. If you take a slice sphere and suspend it, just an ordinary suspension, it's not a slice sphere anymore. It isn't. It's not a slice sphere anymore. And in particular, if you were to take an integer Eilenberg-MacLane spectrum smashed with one of these slice spheres, then that's something called a slice. That's something that could be the nth slice of something. If you take as an ordinary slice and suspend it umpteen times, it's no longer a slice. Figuring out how the slice decomposition of an ordinary suspension of a slice is a topic of ongoing research. People study this thing, write papers about it for various cases.
Can you just say that again? The slice decomposition of the ordinary suspension of a slice.
Yes. Yeah, the slice decomposition of an ordinary suspension of a slice is something that requires some calculation to figure out. That's the way it is. Okay, now I have, so anyway, my third comment is that this is a peculiar spectral sequence because of this failure to commute with suspension. Now, on the other hand, if you were to suspend by smashing with S rho G,
Sure.
then everything would be fine. You're allowed to smash with you're allowed to do regular suspensions, but not ordinary suspensions.
May I ask another question?
Yes.
How do we know that this actually converges to X then, rather than some, I mean, since suspensions of slices aren't slices, it might be that this only sees a part of X and doesn't see all of it.
No, it does. We have a theory.
How do you, why are slices enough to capture everything?
You can show that in this tower here, you can so you have this tower, and you can show that the co-limit, if you go this way, you're going to get all of X.
Well, that's the question, yeah, why? But
Because, all right, I'm sorry, I guess I get that wrong. No, the co-limit is contracted.
I know, but the limit
Okay,
is-
and then the limit is all of X, and yes, you can show that. You can show that.
I guess it's because of regular representations or cofinal, right? I mean,
Something like
sure.
that, yeah,
Right,
something
you
like
take it on
that.
homotopy.
Now, this reminds me, I want to state a theorem that's helpful about this. A theorem that, so we have these subcategories, here, which by definition are subcategories generated by certain slice spheres. Now, if you're looking at a spectrum, it's not easy to figure out which subcategory it's in. This is not so easy, but there's a theorem that makes it a lot easier, which I will state now. Where to do this? So this is due to Hill and Yarnall. And it says the following. X is in the nth subcategory if and only if. Now, the statement is going to involve geometric fixed points, which I haven't defined, and I don't really have time to define, but let's just say geometric fixed points are really cool, and they're a lot more convenient than ordinary fixed points. ordinary fixed points in the world of spectra behave badly for two reasons. Number one, they don't play nicely with smash products. You'd expect that the fixed point of x smash y would be the fixed point of x smash the fixed point of y. It doesn't work that way with spectra. Another thing that another example of bad behavior is you would think that if you're looking at a suspension spectrum, then you'd like to think that its fixed point set is the suspension spectrum of the fixed point set of the space involved. Wouldn't that be nice? Not true, not true. Even, in fact, there's a theorem of Tome Deep that says, take the sphere spectrum with trivial group action on it. Its fixed point spectrum is something you'd never suspect. It's something involving the Burnside ring. Anyway, geometric fixed points don't have these problems. They play nicely with smash products, and they play nicely with infinite suspension. So they're actually much easier to deal with than ordinary fixed points. But here's the deal. So this is a statement that has to hold for every subgroup. For each subgroup of G, and then this is the symbol for geometric fixed points. So geometric fixed points with respect to a subgroup H is a certain ordinary spectrum, so it has ordinary homotopy groups. And what we need is a connectivity condition. And the connectivity condition is you take n and divide it by the order of G. And you want to know that the homotopy groups vanish below that dimension. Now, this may not be an integer. That's okay. K is an integer. And you can talk about inequalities even if you have rational numbers on one side. You still have inequalities. So that's the condition. This, in practice, is much easier to deal with than the original definition. Okay, now the really fun slides are about to start. Yes. Okay, we are looking at the slice spectral sequence for real K theory. KR as conceived by Atiyah. This is a Z2 equivariant spectrum. The underlying spectrum is complex K theory. The fixed point set is real K theory. And this is the slice spectral sequence for it. This was the subject of Dan Duggar's thesis around 2000. And I'm going to take you through this spectral sequence. So this is a spectral sequence of Mackey functors. So there are various symbols that appear here, and they are identified as Mackey functors down here. And these calculations can be made by looking at chain complexes of Mackey functors, as I showed you last time. And okay, so in this case, the order of the group is 2, so the vanishing line has slope 1, and you can see it here. All right, now I'm going to ask you to let's assume that we know this spectrum is 8 periodic. Now, what I'm going to give you isn't actually a proof of that, but I'm not going to prove it. But anyway, I'm going to show you the consequences of being aperiodic, and they are surprising. So let's assume that this spectrum is aperiodic. Now, this picture is certainly not aperiodic. It is certainly not the case that if you slide this picture 8 units to the left or right, you'll get the same picture. This spectral sequence is certainly not aperiodic, but the answer that we're going to get, the actual homotopy of the thing, is aperiodic. So we're going to explore some consequences of that. All right, so here we have a class in dimension 3. This guy right here is a 3-dimensional class. Now, let's look and let's subtract 8 from that and go to -5. Now in -5, there's nothing in -5. Pi minus 5 of this thing is 0. We can see that just from looking at the E1 term of this spectral sequence. This is dimension -5. It's this column here, and there's nothing there, and yet we have something in dimension 3, and I'm asking you to believe that it's aperiodic. So that means this guy in dimension 3 has to go away. So, what do you think happens? It's killed by a differential. Toby, that's in red. Can you see it?
Yes.
Good. Okay, so this differential has to be there because of periodicity. Now, I'm being disingenuous here because in order to prove periodicity, you show that certain differentials happen and blah, blah, blah. So but anyway, this is an interesting argument. If we assume it's aperiodic, then some consequences have to ensue.
Well,
Okay.
as Atia points out, by linear algebra, eta cubed has to be 0.
There's plenty of reasons eta cubed has to be 0, right? But anyway, I'm giving you the reason that the spectrum is aperiodic and pi minus 5 is clearly 0 in this setup. So you have to have this differential. Now, there's enough multiplicative structure around that if you have that differential, you get all of those, and you get all of those. And this pattern extends off to the right in a way that you can
So it's
imagine.
very much like the Boxstein spectral sequence.
Yes.
Does that have that as a sort of quotient or something?
I'm not sure what you mean exactly, but something.
Okay.
Okay, now we're going to play this same game again. We're going to look in dimension -1. Here's dimension -1. See, this thing has this convenient feature that there's this region here where there's very few homotopy groups, no room for differentials or anything, because everything's concentrated on the 0 line. But anyway, we see this is the -1 column, and it's trivial, so pi minus 1 is clearly 0. That means pi minus 9 is 0. Here's a class in dimension -9. So it can't survive, it has to go away. So that means it has to support a differential, and once one differential gets into the party, it brings all its friends. So now we've got a bunch of differentials. Now, the story isn't over yet. This is a spectral sequence of Mackey functors. And the claim is that this is the homotopy of this thing, the homotopy of the spectrum is a graded Mackey functor. And periodicity means periodicity as Mackey functors. So, for example, let's look in dimension -6. In dimension -6, we only have one thing, and it's that symbol there, which is explained here. It's this symbol, this box with a dot over it is a symbol for this particular Mackey functor. And this is a short exact sequence of Mackey functors. And in each case, this is the short exact sequence of Lewis diagrams here. Anyway, this is what happens in pi minus 6. Okay, by periodicity, whatever happens in dimension -6 must also happen in dimension 2. 2 and -6 are congruent mod 8. So pi 2 has to be congruent, has to be isomorphic to pi minus 6. Now, what have we got going on in pi 2? We have two things in this column. We've got a bullet up here and a box bar down here. Now, notice that these two guys are part of this short exact sequence of Mackey functors. So that means that the actual answer is not the direct sum of these two Mackey functors, but this thing in the middle. This is a short exact sequence that isn't split. This short exact sequence isn't split. Now there's a subtlety here, because if you look at this row, this is certainly a split exact sequence. So is this row. This is also a split exact sequence. But if you take into account the additional structure, which are these, you have restriction and transfer maps that are represented by these colored arrows. Green goes down because you're going into the earth, and blue goes up because you're going up into the sky. That's the rationale for this color scheme. The blue maps are transfer, the green maps are restrictions. But anyway, there has to be a transfer map connecting this guy to this guy. There it is. So there's this little blue line here, which means there is actually a non-trivial transfer linking the, if you take the generator of this group down here, its transfer is the generator of this group up here, and there's a jump in filtration. And the same thing happens here by periodicity. Now, there's one more case like this. Let's look in dimension 0. Yes, in dimension 0, we have this guy, the box, which is this Mackey functor. This is known as the constant z-valued Mackey functor. Now, in dimension -8, we have this picture, and it's related to this short exact sequence here. And again, this short exact sequence isn't split at all in any sense because of this. Anyway, what we deduce from that is that, what do we deduce? We deduce that there's a, we deduce that there's a funny restriction map, that the generator of this, this group here, I've lost the thread of this. Green is, what did I say green was? Restriction. Okay, I've lost the thread. But anyway, there is another exotic extension in the Mackey functor structure right here, and similarly here. Now, everything's copacetic. When you throw away everything that's eliminated by differentials, and you take these extensions into account, then it's perfectly periodic. Then it's 8 periodic. And to illustrate that, here's a picture of the E infinity term. I moved them off to the 2nd and 4th quadrants because I have room there. Anyway, this is what the final homotopy groups are. So you can see there are 8 different values. So here's pi 0, pi 1, pi 2, pi 3, pi 4, pi 5, 6, 7, and then 8 is the same thing again. The pattern repeats. And it's the same pattern. The negative dimensional part of it is shown up here. Okay, that is the end of my talk. Thank you.
This period sequence of 8 and the transferring restrictions actually is exactly mirroring Basfield's United K-theory.
I'm not surprised. Yeah. Yeah.
Interesting.
Yeah. So it may be that, I remember Basfield's United K-theory. So it may be that somehow this kind of information might be equivalent to his United K-theory. I don't know.
Well, I think at one point, Stefan Schrader wanted to do a United TMF.
Yeah.
That turned out to be hard, and you had a nice counterexample for the finiteness of the modules that sort of did that in.
Who did?
You did.
I did.
Yeah.
What are you talking about?
No, Lennart was working on this years and years and years ago.
Didn't,
He was hoping to say that there had to be only a finite number, for, in Bouskill's United K-theory, one of the reasons it works is there are only a finite number of sort of indecomposable bits you have to think about. And you actually produced an infinite sequence of examples that showed that that wouldn't work for TMF.
you're sure this was me? I don't.
This is at p equals 3,
Yeah, at p equals 3.
and it just comes out of brackets with alpha.
Okay, if you say so. I don't remember this. Brackets with alpha. Wasn't, I thought Leonard was Leonard's thesis about this, or?
Yep.
Uh-huh. And that didn't, he was,
That approach, taking Bouskill's United K-theory as the model was not actually productive. I think maybe the.
Yeah, that's right.
Pardon?
Yeah, that's right.
Pardon?
I agree.
Oh, okay, yeah.
What happens if you suspend by row G?
what?
What happens if you suspend by row G?
I think you'll see the same picture, and it will be, you have to decide how you want to draw it. See, this is actually an ROG graded spectral sequence. But, okay, ROG in this case is a free abelian group of rank 2, because G is C2. ROG is a free abelian group of rank 2, and then there's the filtration grading, the S grading. So in order to show this thing in its full glory, I need a three-dimensional chart. And I don't know how to make a three-dimensional chart. And even if I did, I'd have to, this is just the C2 case. If I wanted to do C4 or C8, it would get worse. So anyway, this is only showing part of the picture. This is only showing the part where the representation grading happens to be an ordinary integer. Now, there is this nice thing that happens, let's see, in K-theory, you know that multiplication by the equivariant V1, which has degree rho, the regular representation, that's an isomorphism. V1 is invertible in K-theory. So that means that if I were to suspend everything by rho, I get an isomorphic picture. And that means that I really don't, the convenient fact about C2 is that every representation of C2 is some multiple of the regular representation plus an integer. Every representation of C2 differs by an integer from a multiple of the regular representation, and we know that there's this element V1 that has degree rho, and it's invertible in this world. It gives you an isomorphism. So, so that means in this case, all the other charts, if I had to draw them, they'd look exactly the same.
That's the periodic case, right?
Yes.
What happens if you do a connective version?
Well, if you did a connective version, then you'd only see the first quadrant of this. You wouldn't see the.
Okay, that's what connective means here?
Yes. Yeah, it means what you think it means. Yeah. Yeah, you would just see the stuff in the first quadrant. All that stuff off to the left wouldn't be there. Yeah.
Why does it say plastic explosives in the top right?
Very good question.
Oh dear.
Yes.
Should we leave quickly?
Shall we turn
The title of the talk was, let me see if I can get you the title of the talk. When I gave this talk, I thanked the TSA for not reacting to this.
Yes, I see.
Okay, the C4 analog of the Kerr invariant calculation. That's why it's called plastic explosives, the C4. Anyway, there you go. I'm sorry, sorry about that.
Rather cruel.
That's why plastic explosives is in the title. Okay. Any other questions?
Thank you for great lectures.
Switch off the recording.
Oh,
No,
yes.
switch off the recording, right.